Hey friend, welcome. You found a quiet corner of the universe, a place to slow down, breathe, and drift into sleep while learning about the stars. Tonight, we'll explore the Milky Way, our true cosmic home. So get comfortable, let your mind float, and let the galaxy carry you. Chapter 1. What is the Milky Way? A quiet introduction to our galactic home. When you look up into a clear night sky, far from city lights, a faint, milky ribbon stretches across the darkness. For most of human history, no one truly knew what it was. To ancient eyes, it looked like a path of mist, perhaps a celestial river or trail of light left by the gods. The Greeks called it Galaxies Kyklos, the Milky Circle. And centuries later, the Latin name Via Lactea became our modern Milky Way. For millennia, this glowing band was thought to belong to the heavens themselves, not to be made of stars at all. Aristotle imagined it as the reflection of sunlight in the upper atmosphere. Only in the 17th century did Galileo's telescope reveal the truth. The Milky Way is made of countless stars, so distant and numerous that their light merges into a continuous glow. That discovery marked the first step toward understanding the galaxy we live in. Yet even with telescopes, the Milky Way remained mysterious. For hundreds of years, astronomers could not determine its true shape or size. It was only in the early 20th century that Jacobus Kapteyn and Harlow Shapley used measurements of star positions and brightness to map its structure. They found that the sun was not near the center, but rather in the outskirts of a vast, disc-shaped system. Later, radio and infrared observations revealed even more detail. Our galaxy is a barred spiral composed of stars, gas, dust, and invisible dark matter, all rotating together through interstellar space. The Milky Way's form is elegant and complex. At its heart lies a bright central bulge wrapped around a bar of stars. From this bar, spiral arms wind outward like glowing waves. Within those arms are clusters of young, hot stars and vast clouds of gas and dust, the raw material for new generations of suns. The entire disk is only a few thousand light-years thick, but more than 100,000 light-years across. Surrounding it all is a spherical halo containing ancient stars and globular clusters, remnants from the galaxy's earliest days. Beyond that lies an enormous, unseen halo of dark matter that exerts most of the galaxy's gravity. We cannot see this structure directly because we live inside it. From our position about halfway between the center and the outer rim, the Milky Way's disk surrounds us on all sides, and interstellar dust blocks much of the light. But astronomers have found ways to pierce the veil. Radio telescopes trace the glow of hydrogen gas that marks the spiral arms. Infrared observatories like the Spitzer Space Telescope see through the dust to the crowded stars near the core. And the European Space Agency's Gaia mission has mapped the precise positions and motions of more than 1 billion stars, transforming our understanding of the galaxy's shape and motion. Our solar system sits in a minor spur of one spiral arm, known as the Orion arm, between the Sagittarius and Perseus arms. The Sun orbits the galactic center roughly once every 230 million years, a single galactic year. Since its birth about 4.5 billion years ago, it has made only around 20 of those long revolutions. During that time, the galaxy around us has continued to evolve, as stars are born, live out their lives, and die, enriching interstellar space with heavier elements. At the Milky Way's center lies a region of immense power, a supermassive black hole called Sagittarius A star. Hidden behind clouds of dust, it contains about 4 million times the mass of the Sun. Stars near it move at enormous speeds, orbiting an invisible point that gives away the black hole's presence. Although it is mostly quiet today, occasionally it flares as gas and dust fall inward. Sagittarius A star anchors the galaxy's structure, its gravity shaping the orbits of stars throughout the central bulge. The Milky Way is not static. Stars orbit in graceful patterns. Gas clouds drift and collide, and spiral density waves ripple through the disk like gentle tides. Where gas becomes compressed, new stars ignite. Where stars die, supernovae scatter heavy elements into space. Over billions of years, this cycle of creation and destruction has forged every atom in our bodies. The oxygen we breathe, the calcium in our bones, the iron in our blood. In a very real sense, we are fragments of the Milky Way made conscious. The galaxy's history stretches back almost to the dawn of time. It formed about 13 billion years ago from smaller proto-galaxies that merged under gravity. Evidence of those ancient collisions remains today in the halo's old stars and in long, thin streams of stellar debris, the ghostly remnants of galaxies the Milky Way absorbed. Even now, the process continues. The Large and Small Magellanic Clouds, two small satellite galaxies visible from the southern hemisphere, are being slowly pulled apart by our galaxy's gravity. Their stars and gas are stretching into long arcs that wind around us. In the far future, perhaps 4 billion years from now, the Milky Way itself will collide with its great neighbor, the Andromeda Galaxy, merging into a single, larger system. From Earth, we see only a narrow slice of all this complexity. The Milky Way appears as a luminous band across the sky because we are looking along the plane of its disk, seeing layer upon layer of stars. When you look toward the constellation Sagittarius, you face the galactic center, where the density of stars is greatest. Looking toward Cygnus or Cassiopeia takes you outward toward the edges. Every point of light you see is part of the vast structure we inhabit, a glimpse from within of our home in space. Studying the Milky Way is an act of both science and humility. Because we cannot step outside it, astronomers reconstruct its shape through careful observation, measuring distances with parallax, tracing orbits, and modeling how gravity shapes motion. Modern surveys like Gaia have turned this once static picture into a living map, showing how stars stream, oscillate, and even ripple through the disk, echoes of past encounters. Each discovery reminds us that the galaxy is a dynamic system, not a fixed structure, but a constantly evolving one. The Milky Way is also a part of something greater. It belongs to a small family of galaxies called the Local Group, which includes Andromeda and dozens of smaller companions. Together, these galaxies move within an even larger web of cosmic structure, filaments and clusters stretching across the universe. From the largest scales to the smallest atoms, everything in the cosmos is connected by the same laws of physics and by the same cosmic history that began with the Big Bang. Our understanding of the Milky Way deepens every year. Astronomers now study magnetic fields threading through its disk, high-energy bubbles extending above and below the plane, and mysterious flows of dark matter that influence its evolution. Yet for all our measurements, the galaxy retains a quiet mystery. It is both knowable and beyond full comprehension, a reminder that the universe can be studied and yet still inspire awe. When you step outside on a clear night and see the Milky Way arching above you, You are seeing light that has traveled for tens of thousands of years. It left its stars long before human civilization began and crossed interstellar space to reach your eyes tonight. Every photon carries a fragment of the galaxy's story, its birth, its rotation, its endless renewal. You are part of that story, living briefly within a structure that has endured for billions of years. And now, as night deepens and the galaxy drifts overhead, you can let the thought settle quietly. The same gravity that binds its stars together binds you to the earth beneath your feet. The same atoms that once burned in distant suns are within you. The Milky Way is not somewhere far away. It is everything around you, the home that carries you through the endless dark. So breathe deeply, let go of the day, and rest under its calm, eternal light. Chapter 2. The structure of the galaxy, spiral arms, and the galactic disk. From a distance, the Milky Way would appear as a glowing spiral, a great pinwheel of stars suspended in the darkness of space. Its luminous arms curve gracefully outward from a bright central region, forming a structure at once orderly and chaotic. Yet from within, this vast design is almost invisible to us. Dust and distance blur its pattern into a diffuse haze. To piece together the true shape of our galaxy, astronomers have relied on decades of careful observation and inference, mapping what cannot be directly seen. The Milky Way is classified as a barred spiral galaxy, a designation confirmed through infrared observations that reveal a dense, elongated bar of stars at its center. From this bar emerge several spiral arms, which extend outward across the galactic disk. The disk itself is an immense rotating plane of stars, gas, and dust, spanning more than 100,000 light-years from edge to edge, but only a few thousand light-years thick. It is in this thin, luminous layer that most of the galaxy's visible stars reside, along with the complex interstellar medium that gives the Milky Way its form and vitality. The spiral arms are not rigid structures. They are regions of enhanced density, like standing waves in a sea of stars and gas. The stars within them are continually moving, passing in and out of the arms as they orbit the galactic center. The arms persist, not because the same stars remain fixed there, but because density waves, slow-moving gravitational patterns, compress the interstellar medium as they rotate through the disk. This compression triggers new bursts of star formation. Hot, young, massive stars illuminate these regions with brilliant blue light, outlining the arms we see in distant galaxies and indirectly within our own. Our Milky Way contains several major arms. Closest to the center lies the Norma arm, followed by the Scutum Centaurus arm and the Sagittarius arm. Farther out are the Perseus arm and the outer arm. The solar system sits between two of these in a smaller feature known as the Orion Spur or the Orion Cygnus arm. This spur is a minor branch of the larger Sagittarius arm and contains many of the bright constellations visible in our night sky. Each arm is a vast region of gas, dust, and star clusters bound by gravity, yet constantly reshaped by the galactic rotation. The structure of the spiral pattern was first proposed in the mid-20th century, when radio astronomers began mapping the emission from neutral hydrogen gas. Hydrogen emits at a precise radio wavelength, and because radio waves penetrate interstellar dust, these observations allowed astronomers to see deep into the galaxy. By measuring the Doppler shifts of this emission, they determined the distribution of gas and inferred the existence of spiral arms. Later observations in carbon monoxide, a tracer of molecular clouds, provided an even clearer view of the regions where new stars form, confirming that the Milky Way's disk is organized into a majestic spiral pattern. At the center of the Milky Way lies the galactic bulge, a dense, roughly spherical concentration of older stars surrounding the supermassive black hole Sagittarius A star. The bulge transitions outward into the bar, a thick, elongated structure of stars and gas that stretches across tens of thousands of light years. This bar acts as a gravitational engine, funneling gas inward toward the center and outward into the spiral arms. The bar's presence influences the overall dynamics of the disk, helping to sustain the spiral density waves that organize the galaxy's structure. Beyond the spiral arms, the disk gradually thins into the galactic halo, a sparse, roughly spherical region containing ancient stars and globular clusters. While the halo represents the oldest part of the Milky Way, the disk is where the ongoing processes of star birth and death continually reshape the galaxy's appearance. Within the disk, massive clouds of gas collapse under gravity to form new stars. When those stars die in supernova explosions, they enrich the surrounding gas with heavier elements, which are later incorporated into new generations of stars and planets. Over cosmic timescales, this recycling has built up the chemical complexity that makes life possible. The vertical structure of the disk is as fascinating as its spiral form. Astronomers distinguish between a thin disk and a thick disk, two overlapping populations of stars with different ages and compositions. The thin disk contains younger stars, open clusters, and much of the interstellar gas and dust. It is where star formation is most active. The thick disk, extending farther above and below the galactic plane, contains older stars with fewer heavy elements, relics from the early history of the galaxy, likely formed when it was still merging with smaller protogalaxies. The existence of these two disks tells a story of gradual evolution. The Milky Way began as a chaotic assembly of gas clouds and smaller galaxies, which over time flattened and stabilized into the ordered, rotating disk we inhabit today. Rotation itself is a key to understanding the galaxy's structure. Every star and gas cloud orbits the galactic center, but not in the same way planets orbit the sun. The outer parts of the galaxy rotate almost as fast as the inner regions, a phenomenon known as flat rotation. This observation was one of the earliest clues to the existence of dark matter, an unseen form of mass that dominates the galaxy's total gravitational pull. Without dark matter, the stars in the outer disk would not have enough gravity to keep them bound to the Milky Way. Their high orbital speeds would tear the galaxy apart. The persistence of the flat rotation curve implies that an enormous invisible halo of dark matter extends far beyond the visible disk, shaping its dynamics and holding it together. The disk itself is not perfectly smooth. It bends and ripples, warped like a vast sheet of fabric stirred by unseen winds. Surveys of distant stars and gas clouds have revealed that the Milky Way's outer regions curve upward on one side and downward on the other. This warp may have been caused by gravitational interactions with nearby satellite galaxies, such as the Magellanic Clouds, or by the uneven distribution of dark matter in the halo. The warp gives our galaxy a subtle, asymmetric shape, a reminder that even large cosmic systems are never entirely at rest. Within the spiral arms, star formation occurs in bursts. Dense molecular clouds collapse under their own gravity to form clusters of newborn stars. The most massive of these stars live fast and die young, Their ultraviolet radiation and stellar winds blowing bubbles and cavities into the surrounding gas. When they explode as supernova, they trigger further waves of collapse, spreading star formation through the arm like a slow-moving flame. This process gives the Milky Way its patchwork of bright nebulae, glowing regions of ionized gas, and dark lanes of dust that obscure the starlight behind them. The interstellar medium within the disk is a complex mixture of gas, dust, and plasma, existing in several distinct phases: cold molecular clouds, warm atomic gas, and hot ionized regions created by stellar radiation. This mixture is far from uniform. It is constantly stirred by shock waves, magnetic fields, and turbulence on every scale. The interplay between these forces creates the structures we observe: filaments, shells, and cavities that make the galactic disk a living, dynamic environment. Modern astronomical surveys have transformed our understanding of the Milky Way's structure. Data from the Gaia spacecraft have mapped the positions and velocities of more than 1 billion stars, allowing scientists to reconstruct the galaxy's three-dimensional shape with unprecedented precision. These observations have revealed ripples in the disk, subtle vertical waves in the distribution of stars, possibly caused by ancient collisions with smaller galaxies. Other studies using infrared telescopes have confirmed the bar's orientation and the pattern of the spiral arms. Step by step, a coherent picture has emerged. The Milky Way is a rotating, self-sustaining system, shaped by gravity, motion, and time. From a cosmological perspective, the Milky Way's structure reflects a universal pattern. Spiral galaxies like ours make up the majority of large galaxies in the observable universe. Their disks form naturally as gas cools and settles into rotation within dark matter halos. The balance between gravity and angular momentum shapes them into flattened rotating systems with spiral patterns that arise from density waves. Though each galaxy is unique, the same physical principles govern them all. The Milky Way, in that sense, is both ordinary and extraordinary, a familiar example of the universe's artistry. For those living within it, the Milky Way's structure offers both a map and a metaphor. We occupy a small neighborhood within one of its minor arms, circling quietly as part of a vast gravitational dance. Every star you see in the night sky belongs to this same disk, each moving along its path in harmony with billions of others. The spiral arms, though invisible from the ground, define the great architecture that has shaped our cosmic environment for billions of years. If one could look upon the Milky Way from afar, perhaps from the perspective of an intergalactic traveler, it would appear serene, a swirl of light against the dark. Yet, within that calm exterior lies unending motion. The orbits of stars, the turbulence of gas, the pulse of radiation, and the slow evolution of form. What we call structure is, in truth, a balance between chaos and order, maintained across incomprehensible spans of time. When we reflect on this, a quiet realization emerges. The galaxy's spiral pattern, so vast it takes hundreds of millions of years to complete a single turn, is the setting of our entire history. Every life, every memory, every thought. We exist as part of a disk of stars that has endured for more than 10 billion years, held together by the same gravity that holds us to the Earth. To contemplate the structure of the Milky Way is to recognize our place in something enduring and immense. And as the galaxy turns, carrying us through the silent dark, there's a strange comfort in its permanence. The spiral arms will continue to wind, the disk will continue to spin, and the starlight will continue to flow long after our brief stories have ended. Beneath that endless motion, you are part of the pattern, a fleeting awareness born of the same forces that shape the stars. Chapter 3. The Heart of the Galaxy, the Supermassive Black Hole, Sagittarius A. At the very center of the Milky Way, hidden behind dense clouds of interstellar dust, lies a place where ordinary physics breaks down. It is a region of such immense gravity that nothing, not even light, can escape its grasp. This is Sagittarius A star, the supermassive black hole that anchors our galaxy. Although invisible, it shapes the motion of millions of stars, governs the dynamics of the galactic core, and serves as the quiet heart around which the Milky Way revolves. For centuries, the idea of a cosmic abyss was little more than a mathematical curiosity. When Albert Einstein formulated his general theory of relativity in the early 20th century, the equations suggested the possibility of points where gravity could become infinite. Karl Schwarzschild, working only months after Einstein's publication, derived a solution describing a perfectly spherical object with an escape velocity greater than the speed of light. Such an object, though purely theoretical at the time, would later be called a black hole. It took decades, however, for astronomers to accept that these extreme structures might actually exist. The Milky Way's central region was long thought to contain something massive and unseen. Observations in visible light were useless. The dense clouds of gas and dust in the galactic plane absorbed nearly all optical radiation from the center. It was only with the development of infrared and radio astronomy that scientists could peer through the obscuring material. In the 1970s, powerful radio telescopes detected a compact, bright source of radio waves near the constellation Sagittarius, precisely at the galactic core. They named it Sagittarius A star. Over the following decades, increasingly precise measurements revealed something extraordinary. Stars near the center of the galaxy were moving at incredible speeds, some thousands of kilometers per second, in tight elliptical orbits around an invisible point. By tracking these orbits over many years, astronomers were able to calculate the mass of the object exerting such powerful gravitational influence. The result was astonishing. Roughly 4 million times the mass of the Sun, confined within a region no larger than our solar system. There was no known object that could fit those conditions except a black hole. The most compelling evidence came from long-term observations by two teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, and the other by Andrea Ghez at the University of California, Los Angeles. Using adaptive optics and interferometry, they tracked the motion of individual stars orbiting the galactic center over decades. One of these stars, called S2, moves so close to the center that it completes an orbit in just 16 years. A mere blink compared with the Sun's galactic circuit of hundreds of millions of years. The precise shape of its orbit confirmed Einstein's predictions of general relativity. The immense mass and compact size of the central object left no doubt. Sagittarius A star is a supermassive black hole. A black hole itself emits no light. What astronomers detect comes from the material around it, gas, dust, and occasionally entire stars that venture too close. As matter falls toward the event horizon, it accelerates and heats up, glowing intensely in X-rays and infrared radiation. This glowing region, known as the accretion disk, marks the boundary between the observable universe and the domain of gravity so strong that space and time fold inward. In the case of Sagittarius A star, the accretion disk is faint compared with those of more active black holes in distant galaxies. The Milky Way's central black hole is considered quiescent, feeding only sporadically on the trickle of gas and dust that drifts into its vicinity. Despite its quiet nature, Sagittarius A star occasionally flares. Infrared and X-ray observatories such as Chandra and the Very Large Telescope have recorded sudden bursts of radiation, brief but powerful flashes that last for minutes to hours. These are thought to occur when clumps of matter are caught in the black hole's gravitational whirlpool and heated to millions of degrees before disappearing beyond the event horizon. Though these flares reveal only fleeting glimpses of activity, they confirm that the black hole remains a living, dynamic engine at the heart of the galaxy. The region surrounding Sagittarius A star is a unique laboratory for studying the extreme conditions of physics. Within a few light-years of the black hole lies a dense cluster of stars, many of them massive and short-lived. Their presence is somewhat paradoxical. Conditions near a black hole should be hostile to star formation, yet evidence suggests that stars continue to form there, possibly in dense rings of gas orbiting just beyond the reach of destruction. These stellar populations, along with the intricate orbits mapped by missions like Gaia and the Keck Observatory, allow scientists to test the predictions of general relativity in the most extreme gravitational environment accessible to observation. In 2019, the Event Horizon Telescope, a network of radio observatories spread across the Earth, captured the first direct image of a black hole's shadow in the galaxy Messier 87. 3 years later, the same collaboration produced an image of Sagittarius A star. The image showed a bright, ring-like structure of light surrounding a dark central region, the shadow of the event horizon, distorted by the intense warping of space-time. It was not a photograph in the conventional sense, but rather a reconstruction derived from global interferometry, translating faint radio signals into an image of what lies at the center of our galaxy. That ring, only about 60 million kilometers across, represents the final surface from which light can still escape before plunging into the black hole itself. What lies beyond the event horizon remains unknown. According to general relativity, the matter that falls into a black hole collapses to an infinitely dense point called a singularity, where the laws of physics as we know them cease to apply. Quantum theory, however, suggests that this picture is incomplete, that information and energy cannot be lost entirely. Reconciling these two frameworks is one of the deepest challenges in modern physics. Sagittarius A star, though small on cosmic scales, sits at the crossroads of these mysteries. It is a reminder that our understanding of the universe remains unfinished, even in the heart of our own galaxy. The black hole's influence extends far beyond its immediate surroundings. Although its gravitational pull dominates only the inner few light years, it shapes the dynamics of the entire galactic bulge and may help regulate star formation in the central regions. Evidence from other galaxies shows that supermassive black holes and their host galaxies evolved together, their masses growing in proportion over cosmic time. This suggests a profound connection. The processes that feed black holes also drive the formation of stars and the distribution of gas in galaxies. In this sense, Sagittarius A star is not merely a passive anchor, but an active participant in the Milky Way's evolution. Astronomers studying high-energy phenomena have also discovered vast structures extending from the galactic center, the so-called Fermi bubbles, enormous lobes of energetic gas, stretching tens of thousands of light-years above and below the galactic plane. These bubbles are believed to be relics of a past episode of intense activity, when Sagittarius A star may have accreted large amounts of matter and released powerful jets of radiation. Though dormant now, the black hole once blazed brightly, influencing the galaxy on scales far beyond its immediate reach. Despite its reputation as a cosmic monster, Sagittarius A star is not a threat to us. The solar system lies nearly 26,000 light-years away, safely beyond its gravitational influence. The light and radiation it emits are too faint to affect our planet. What it represents, rather than danger, is a window into the extreme nature of the universe, a living example of the balance between gravity, energy, and the limits of physical law. From a scientific perspective, the study of Sagittarius A star is a triumph of observation and theory. From the first radio detections to the detailed tracking of stellar orbits, each step has confirmed predictions of Einstein's equations with remarkable precision. The black hole's measured properties, its mass, spin, and event horizon, match the theoretical expectations for a rotating Kerr black hole. Yet the closer we look, the more profound the questions become. What happens to information that crosses the horizon? Can gravity and quantum mechanics ever be unified into a single description? Could the singularity itself be something more complex than an infinitesimal point? While physicists debate these questions, Sagittarius A star continues its silent existence, shaping space and time without a sound. It is an object of perfect stillness and ultimate energy, where the geometry of the universe folds back upon itself. Around it, stars continue to orbit like dancers circling an unseen partner, each motion a testament to the invisible mass at the center. To contemplate this heart of darkness is to glimpse both the power and the humility of nature. Our galaxy, with all its spiral arms, stars, and planets, revolves around a point of nothingness, an emptiness that defines the whole. The Milky Way's beauty and stability arise paradoxically from a region where matter ceases to exist as we understand it. It is a reminder that creation and destruction are not opposites, but two faces of the same cosmic process. And perhaps that realization offers a kind of peace. The same gravity that holds the stars together also holds us, weaving everything into a single story that began long before we existed. Sagittarius A star, silent and invisible, is not only the heart of the galaxy, but a symbol of continuity. The balance between what can be known and what forever remains beyond the horizon. As you think of it, far away in the darkness, you might feel that quiet gravity too, drawing all things toward unity, reminding us that even in the vastness of space, we are part of something whole. Chapter 4. The Stars of the Milky Way, From Newborns to Dying Giants. The Milky Way is not merely a collection of stars scattered through space. It is a vast, living system where stars are constantly being born, aging, and dying. Within its disk and halo exist hundreds of billions of suns, each at a different point in its life cycle, each a luminous thread in the great tapestry of our galaxy. From cool red dwarfs that burn slowly for trillions of years to colossal blue giants that exhaust their fuel in only a few million, the stars of the Milky Way form the structure, chemistry, and destiny of our cosmic home. The story of every star begins in darkness. Deep within cold molecular clouds, Enormous regions of gas and dust scattered through the galactic disk, gravity slowly draws matter together. Over thousands of years, the densest knots of gas collapse under their own weight, forming protostars surrounded by disks of dust. These regions are invisible in visible light, but glow in infrared, where observatories like the James Webb Space Telescope can peer through the obscuring dust. The Orion Nebula and the Eagle Nebula are famous examples. Stellar nurseries where young suns ignite and sculpt their surroundings with intense radiation. When the temperature at the core of a forming star becomes high enough, hydrogen nuclei begin to fuse into helium. This process releases vast amounts of energy, halting further collapse and creating a delicate balance between gravity pulling inward and radiation pushing outward. A true star is born. The newborn star settles onto what astronomers call the main sequence, a stable phase of life that can last millions to billions of years, depending on its mass. Most of the Milky Way's stars are small, dim red dwarfs. These low-mass stars burn hydrogen slowly and efficiently, their lifetimes measured not in billions but in trillions of years, far longer than the current age of the universe. They make up the quiet majority of our galaxy, unseen to the naked eye, but dominating by sheer number. Their faint light fills the galactic disk like a low, constant hum, sustaining the structure of the Milky Way through their collective gravity. At the other extreme are the massive blue and white stars, giants several tens of times heavier than the Sun. They live fast and die violently. Their cores burn at immense temperatures, fusing heavier and heavier elements in rapid succession. In just a few million years, these giants exhaust their fuel, collapse under their own weight, and explode as supernovae. Such explosions briefly outshine entire galaxies, dispersing the elements forged in their cores, carbon, oxygen, calcium, and iron, into the surrounding interstellar medium. Every atom of iron in your blood was once released by a supernova like these. Between these two extremes lie the sun-like stars, medium in mass and longevity. They spend most of their lives fusing hydrogen into helium in a steady rhythm. When their central hydrogen runs low, the balance between gravity and pressure falters. The core contracts while the outer layers expand, transforming the star into a red giant. In this stage, the star's outer atmosphere swells to enormous size, sometimes engulfing nearby planets. The Sun will follow this path in about 5 billion years, eventually shedding its outer layers into space to form a glowing planetary nebula. The remaining core will cool into a white dwarf, a dense remnant roughly the size of Earth, but containing half the Sun's mass, glowing faintly as it radiates away its stored heat over billions of years. The diversity of stars within the Milky Way reflects the galaxy's long and complex history. The oldest stars, bound in the halo and globular clusters, are poor in heavy elements. These ancient suns formed soon after the galaxy itself was born, before successive generations of supernovae enriched the interstellar medium with metals. They are fossils of the early universe, their composition a record of the Milky Way's first epoch of star formation. In contrast, stars in the thin disk, including the Sun, are metal-rich, having formed from gas already seeded with the products of countless previous stars. This gradient in metallicity allows astronomers to trace the timeline of galactic evolution, reading it like tree rings written in starlight. Star clusters are another window into the structure and history of the Milky Way. Open clusters, such as the Pleiades, contain hundreds of young stars born from the same cloud. Their ages can be measured precisely, making them invaluable for calibrating models of stellar evolution. Globular clusters, by contrast, are densely packed spheres of hundreds of thousands of very old stars, orbiting far above and below the galactic disk. They are among the oldest surviving structures in the galaxy, remnants of the Milky Way's early assembly. Stars are not evenly distributed throughout the Milky Way. They are concentrated in the spiral arms, where density waves compress gas clouds and trigger bursts of star formation. Within these regions, massive stars form in clusters, light up the surrounding nebulae, and then die young, often before they have drifted far from their birthplaces. Their deaths enrich the nearby gas, and the cycle begins anew. Meanwhile, the older stars gradually drift out of the arms into the more diffuse background of the disk. The entire galaxy is thus engaged in a constant process of renewal, recycling its material through countless stellar generations. The physics of a star's life and death is governed by its mass. Mass determines the balance of gravity and pressure, the rate of nuclear fusion, the lifetime, and the manner of death. Low-mass stars end quietly as white dwarfs. Massive ones collapse to neutron stars or black holes. Neutron stars, the remnants of particularly massive explosions, are among the densest objects in the universe, composed almost entirely of neutrons packed into a sphere barely 20 kilometers across. Some of them spin rapidly, emitting beams of radiation like cosmic lighthouses known as pulsars. Others merge in cataclysmic collisions that generate gravitational waves and forge the heaviest elements, such as gold and platinum. The interplay between stellar birth and death defines the Milky Way's evolution. Each generation of stars alters the chemical and physical state of the interstellar medium, setting the conditions for the next. The galaxy's current star formation rate is estimated at about 1 or 2 solar masses per year, a steady pace that maintains its luminous population without exhausting its gas too quickly. This balance between consumption and renewal has persisted for billions of years, giving rise to the rich and varied stellar ecosystem we observe today. Advances in observational astronomy have deepened our understanding of this process. Space telescopes such as Hubble and James Webb allow astronomers to observe stellar nurseries in exquisite detail, revealing how dust grains clump into protostellar disks and how jets of plasma erupt from newborn stars. Meanwhile, surveys from missions like Gaia have mapped the motions of stars across the galaxy, uncovering streams and clusters that hint at past mergers and migrations. Through these data, the Milky Way emerges not as a static collection of stars, but as a dynamic, self-renewing organism on cosmic scales. Stars also serve as cosmic clocks. By analyzing their light, its color, brightness, and spectral lines, scientists can determine their age, composition, and distance. The Hertzsprung-Russell diagram, which plots stars by temperature and luminosity, provides a universal framework for understanding stellar evolution. It shows that the life of every star follows predictable paths dictated by physics, from the moment of ignition to the final fade into darkness. The same laws apply to all stars, from the smallest red dwarfs to the brightest supergiants, linking the Milky Way's billions of suns through a single underlying order. Yet for all this order, there remains something deeply human about the light of the stars. Every photon that reaches us carries information about its source, the temperature, motion, and history of the star that emitted it. When that light enters your eyes, you are, in a sense, touching the past. The glow of Vega left that star more than 2 decades ago. The shimmer of Deneb began its journey more than 1,000 years earlier. The night sky is not a fixed dome but a time machine, showing us the Milky Way as it was across different epochs of history. Beyond their physical properties, stars have also been mirrors for human thought. For ancient civilizations, they served as calendars and guides. For modern science, they are laboratories of matter and energy. But their deeper significance lies in what they reveal about our origins. Every element essential for life, carbon, nitrogen, oxygen, and iron, was born in stars and scattered across space. When you look at the Milky Way, you are seeing not only distant suns, but also the source of your own existence. The same nuclear reactions that burn in those stars once forged the materials of your body, and in the grand cycle of time, those materials will one day return to the galaxy. The atoms that compose you will be dispersed again, perhaps drawn into new clouds, new stars, new worlds. The Milky Way is a vast, continuous act of creation, in which every ending feeds another beginning. Its stars are the rhythm of that cosmic heartbeat, pulsing in light and silence across the ages. So as you look at the sky, at the faint shimmer that stretches from horizon to horizon, remember that you are part of it. The same forces that ignite stars also shape you. The same elements that glow in their hearts flow in your veins. The stars of the Milky Way are not distant strangers but ancient relatives, bound to you through time and matter. Their births and deaths are your story, written on a scale too large to imagine, yet close enough to feel in every breath. The galaxy's stars remind us that existence is a cycle, not a line. Every atom that shines, burns, or fades is part of a greater pattern. The endless transformation of energy into form and form back into energy. The Milky Way itself, for all its grandeur, is just one chapter in that ongoing story. And within it, you are a brief flicker of awareness, a momentary spark reflecting the light of billions of suns. To understand the stars is to glimpse that quiet truth, that you, too, are a way for the universe to look back at itself and see that it shines. Chapter 5. The Galactic Ecosystem, Gas, Dust, and the Birth of New Stars. Between the stars of the Milky Way lies an ocean of invisible material, a delicate mixture of gas, dust, and plasma known as the interstellar medium. Though tenuous by earthly standards, this medium is the raw material from which stars and planets form, and it is the thread that connects every generation of celestial bodies. The Milky Way is not simply a static collection of stars. It is an evolving ecosystem, where the death of old stars enriches the medium and the birth of new ones continues the cycle of creation. The interstellar medium is composed primarily of hydrogen and helium, the simplest and most abundant elements in the universe. But mixed within this gas are traces of heavier elements, carbon, oxygen, silicon, and iron, forged in the hearts of dying stars and distributed through space by supernova explosions. These elements condense into microscopic dust grains that drift through the galactic disk, absorbing and scattering light. It is this dust that gives the Milky Way its dark lanes and obscuring clouds, shaping what we can and cannot see. Although the average density of the interstellar medium is far lower than the best vacuum on Earth, its vast volume means it contains a tremendous amount of mass. Roughly 15% of the visible matter in the galaxy. It is structured not as a uniform mist, but as a complex network of clouds, filaments, and bubbles, all in motion. These structures form, dissipate, and reform over millions of years under the influence of gravity, magnetic fields, and stellar feedback. The most important regions of this galactic ecosystem are the molecular clouds. These are cold, dense concentrations of gas and dust, where temperatures fall to just a few tens of degrees above absolute zero. Under such conditions, hydrogen atoms bind together to form molecular hydrogen, the most basic building block of star formation. Within these clouds, gravity begins its quiet work. Tiny fluctuations in density cause certain regions to collapse, drawing in more material as they do. Eventually, these collapsing pockets become protostars, the seeds of future suns. Astronomers map these molecular clouds using radio telescopes, since visible light cannot penetrate their thick dust. The emission from carbon monoxide molecules, in particular, provides a reliable tracer of their structure. Observations of regions such as the Orion molecular cloud reveal a dynamic environment where turbulent gas streams and shock waves from nearby stars sculpt the clouds into intricate shapes. These regions are often several light-years across and contain enough material to form thousands of stars. The process of star formation is slow and inefficient. Most of the gas in a molecular cloud never becomes a star. Instead, stellar winds, radiation pressure, and supernova explosions from nearby massive stars disrupt the cloud before it can fully collapse. Yet these same forces also play a creative role, compressing other regions of gas and triggering new waves of star formation. In this way, the death of one generation of stars can give birth to the next. The Milky Way continually recycles its material, maintaining a delicate balance between destruction and renewal. This balance can be seen in the life cycle of the interstellar medium itself. Hot ionized gas from supernova remnants expands into the surrounding space, creating vast bubbles that sweep up cooler material into dense shells. Over time, these shells cool and fragment into molecular clouds, where new stars ignite, releasing radiation that heats and stirs the surrounding gas once again. The result is a galactic web of feedback loops, where every phase of matter influences the others. The galaxy is, in essence, a self-regulating ecosystem, operating on scales of light years and millions of years. Dust, though it makes up only a tiny fraction of the mass, plays an essential role in this ecosystem. It provides the surfaces on which molecules can form, shields the interiors of clouds from destructive ultraviolet radiation, and determines how starlight is absorbed and re-emitted across the spectrum. Infrared observations have revealed vast networks of dust filaments tracing the magnetic fields of the galaxy, showing that even the smallest particles contribute to the Milky Way's structure and energy balance. Without dust, the chemistry that leads to complex molecules and eventually to life could not occur. The Milky Way's spiral arms act as engines driving this cycle. As density waves sweep through the galactic disk, they compress gas clouds, initiating new rounds of star formation. In these regions, bright clusters of young, massive stars illuminate nearby nebulae, such as the Carina and Eagle nebulae, turning cold gas into radiant clouds of ionized hydrogen. The light from these stellar nurseries can travel thousands of light years, marking the spiral arms as bands of blue and pink that define the galaxy's graceful form. Not all interstellar gas remains within the plane of the disk. Powerful supernovae and stellar winds can push material into the galactic halo, forming what astronomers call galactic fountains. The hot gas rises far above the disk, cools as it radiates energy, and eventually falls back, raining fresh material onto the galaxy. This circulation helps maintain the Milky Way's supply of star-forming gas over cosmic timescales, linking the visible disk with the more diffuse environment that surrounds it. At larger scales, the Milky Way also interacts with the intergalactic medium, the thin gas that fills the space between galaxies. Observations from the Hubble Space Telescope and other observatories have revealed extended halos of gas around the Milky Way and its neighbors, stretching for hundreds of thousands of light years. These halos serve as both reservoirs and regulators, storing gas that may one day cool and return to the disk. The boundaries between the Milky Way and its environment are therefore porous, blurring the distinction between galaxy and cosmos. The chemical evolution of this galactic ecosystem is equally fascinating. Each generation of stars enriches the interstellar medium with new elements. The first stars, massive, short-lived giants formed shortly after the Big Bang, contained almost no metals. Their violent deaths seeded the early universe with carbon, oxygen, and other elements, enabling subsequent generations of stars to form planets and eventually life. In the Milky Way today, the metallicity of the gas varies from one region to another, reflecting the history of enrichment and mixing across billions of years. This distribution allows astronomers to trace how the galaxy has grown and evolved through mergers and accretion events. Understanding the interstellar medium is also essential for understanding the conditions that lead to habitable worlds. Planets form within the dusty disks surrounding young stars, and the composition of that dust determines what materials are available for building solid worlds and organic molecules. The carbon-to-oxygen ratio in the gas, the abundance of water and silicates, and the prevalence of heavy elements all influence the types of planets that emerge. Thus, the chemistry of the galaxy's gas and dust sets the stage for the potential of life itself. Modern astronomy continues to refine this picture with unprecedented detail. Radio arrays such as ALMA in Chile reveal the fine structure of molecular clouds and the earliest stages of star formation. Infrared and submillimeter observations trace the distribution of dust and the glow of warm gas, while X-ray telescopes detect the hot plasma left by supernova explosions. Together, these instruments show that the Milky Way is an interconnected system where energy flows from stars into space and back again in endless cycles. Despite its vastness, the interstellar medium operates under universal physical laws. The same processes that shape the Milky Way occur in countless other galaxies across the universe. Yet from our position within this one, we can observe the details of how those processes work, how gravity, turbulence, and radiation interact to turn chaos into order, darkness into light. Every nebula, every glowing cloud, every faint wisp of dust is part of this grand transformation. To grasp the galactic ecosystem is to recognize that the Milky Way is alive in a metaphorical sense. It breathes through cycles of creation and destruction, nourishes itself through the recycling of matter, and evolves as its components exchange energy and mass. The light of the stars, the coldness of the clouds, and the silence between them are all part of one continuous process, unfolding on a time scale that dwarfs human existence. And yet, within that vast process, there is intimacy. The oxygen in your lungs and the carbon in your cells were once part of the interstellar medium, atoms that drifted through the galaxy for billions of years before becoming part of you. When you exhale, those same atoms will return to the air and eventually to the cosmos. The cycle continues, unbroken. You are part of the Milky Way's ecosystem as surely as the stars and clouds are. Perhaps that is the quiet lesson of the galaxy's dust and gas, that life itself is not separate from the universe, but a natural extension of it. The same physical laws that govern the birth of stars also govern the chemistry of your body. The same hydrogen that collapses to form suns flows through your veins as water. You are, in a very real sense, the galaxy made conscious, a fleeting awareness within a process that has no beginning or end. The Milky Way's ecosystem is therefore more than an astronomical phenomenon. It is a reflection of continuity, of connection across scales so vast that they dissolve the boundaries between the cosmic and the personal. To study the gas and dust between the stars is to study the origin of everything familiar, the atoms of our planet, our breath, our thoughts. When you look up at the hazy glow of the Milky Way, remember that its light and your life are drawn from the same source, woven from the same ancient matter. And in that realization, there is a kind of peace, the knowledge that nothing in the universe is truly isolated, that all things, even we, are part of one continuous exchange of energy, endlessly returning to the stars. Chapter 6. Our place in the galaxy, the solar system's journey through space. The solar system is not fixed in the cosmos. It moves, carried through the Milky Way as part of a vast gravitational dance. Every star you see in the night sky, every cloud of gas or trace of dust is taking part in this same motion, orbiting the galactic center in a rhythm that has endured for billions of years. Our sun, with its family of planets, is one of hundreds of billions of travelers following ancient, curved paths through space. The sun resides in a quiet region of the Milky Way known as the Orion Spur, a minor branch located between two major spiral arms, the Sagittarius arm and the Perseus arm. From this position, about halfway between the center of the galaxy and its outer edge, the sun orbits around the Milky Way's core. The distance is immense, and one complete orbit takes roughly 230 million years, what astronomers call a galactic year. Since its formation, the sun has made only about 20 such revolutions. This orbit is not a perfect circle, nor does it lie flat. The solar system moves in a gentle wave, bobbing above and below the galactic plane over tens of millions of years. These oscillations are caused by the gravitational pull of the Milky Way's disk, made up of stars, gas, and dark matter. Like a pebble rolling in a shallow bowl, the sun is continually drawn back toward the galactic midplane. This motion, subtle and slow, is part of the broader gravitational choreography that gives the Milky Way its balance and shape. As it travels, the sun carries with it all of its planets, comets, and asteroids, an entourage bound together by the same gravity that keeps Earth in orbit. Together, we race through space at hundreds of kilometers per second, though from our vantage point on Earth, that motion is imperceptible. The stars appear still because of their great distances, but they too are moving, each following its own orbit around the galactic center. Over the course of millions of years, constellations change shape, and familiar patterns in the sky fade and reform as the galaxy slowly turns. Our solar system is currently embedded in a region of space known as the local bubble, a cavity of thin, hot gas that stretches for roughly 1,000 light years. This bubble was carved by a chain of ancient supernova explosions that swept away denser interstellar gas. Within this zone, the solar system drifts through a relatively calm environment, protected by the sun's own magnetic field and the solar wind. a steady stream of charged particles that creates the heliosphere. The heliosphere acts as a vast shield, deflecting much of the cosmic radiation that flows through the galaxy. At its farthest edge lies the heliopause, the true boundary where the sun's influence ends and interstellar space begins. The Voyager spacecraft have crossed that frontier, becoming humanity's first emissaries beyond the sun's protective bubble. The path the solar system follows through the Milky Way is not constant. As it orbits the galactic center, it occasionally passes through regions of higher stellar density, spiral arms filled with young stars and gas clouds, and then emerges into quieter interarm zones. These encounters can have subtle but lasting effects. When the sun moves through dense molecular clouds or passes near supernova remnants, the increase in cosmic rays could influence the solar system's outer regions or even the Earth's atmosphere. Though such events occur over immense timescales, they are reminders that our planetary system is part of a larger, dynamic environment. The sun's current neighborhood consists of stars that share similar galactic orbits. This region is called the local stellar neighborhood, containing familiar systems like Alpha Centauri, Sirius, and Barnard Star. But these companions are temporary. Over millions of years, as each star moves along its own orbit, our neighbors will change. The sun's path through the galaxy continually reshapes its surroundings, ensuring that the sky above Earth is never truly the same from one cosmic epoch to the next. At the center of our journey lies Sagittarius A star, the supermassive black hole that anchors the Milky Way. Though its gravity exerts little direct pull on the sun compared to nearby stars, it defines the structure of the entire galaxy. The sun's orbit, like those of all other stars, is ultimately a response to the deep gravitational well at the galactic core. Every turn we make through the galaxy is part of the same vast rotation governed by that invisible center, where gravity bends space and time into harmony. From our vantage point, we cannot see the full spiral of the Milky Way, only a cross-section of its disk stretching across the night sky. Yet our position is a fortunate one. Closer to the center, the environment is far more hazardous, crowded with stars and intense radiation. Farther out, there would be fewer heavy elements, the materials needed for rocky planets and life. The sun's orbit through this relatively calm and metal-rich region has likely provided the stability necessary for life to emerge and endure on Earth. The motion of the solar system also reveals itself through the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. By measuring slight shifts in that radiation, astronomers can determine our velocity relative to the rest of the cosmos. These observations confirm that not only are we orbiting within the Milky Way, but the galaxy itself is in motion, drawn toward neighboring galaxies in the local group and, on even larger scales, flowing toward clusters of galaxies that shape the structure of the universe. Every object, from the smallest moon to the largest supercluster, participates in this grand movement, all bound by gravity's unbroken web. The solar system's galactic journey has unfolded for billions of years and will continue for billions more. Long after the human species has passed, long after the sun expands into a red giant and then cools into a white dwarf, the remnants of our system will keep circling the Milky Way, completing orbit after orbit in silence. Even as the galaxy itself evolves, merging one day with Andromeda to form a new, larger galaxy, the fragments of our home will still be moving through the same gravitational dance that began when the Milky Way was young. To recognize our motion through the galaxy is to change how we see ourselves. We live our daily lives on a planet that spins around its axis and orbits the sun. But those motions are nested within even greater ones: the solar system orbiting the galactic center, the galaxy itself flowing through the cosmic web. Every moment of stillness we feel is an illusion created by scale. Beneath that calm, we are always moving, carried by currents of space and time too vast to perceive directly. The knowledge that we are travelers within the Milky Way can feel both humbling and profound. Our lives, measured in years, unfold within a galactic orbit measured in hundreds of millions. Yet within that brief instant, consciousness has arisen, capable of understanding the motion of its own home, of mapping the invisible paths of stars, of looking outward and realizing that it too belongs to the great rotation. When you look up at the Milky Way on a clear night, you are seeing the trail of your journey, the luminous band that marks the disk through which you travel. Each point of light is a fellow voyager, another sun caught in the same flow. The galaxy turns slowly, steadily, with a grace that feels eternal. And though your time within it is brief, you are part of that movement, bound to the stars by the same force that shapes them. In that thought, there is a quiet comfort. You are not still, not separate, but part of an endless voyage that began long before you and will continue long after. The earth beneath you spins, the sun carries you through the Milky Way, the galaxy itself drifts through the universe. All motion, all time, all existence are one continuous current. And somewhere within that current, small, luminous, and aware, you are moving too. Chapter 7. The Hidden Halo, Dark Matter and the Galaxy's Invisible Mass. The Milky Way, for all its luminous beauty, is not what it seems. The glowing spiral of stars that we see in the night sky represents only a small fraction of what truly exists. Surrounding our galaxy is an enormous invisible structure known as the dark matter halo, a vast, roughly spherical region of unseen mass that extends far beyond the visible disk. It is this halo, rather than the stars or gas, that provides most of the galaxy's gravitational strength. Without it, the Milky Way would not hold together. Its stars would drift apart into the emptiness of intergalactic space. Dark matter is one of the deepest mysteries in modern astrophysics. It neither emits nor absorbs light, making it undetectable through ordinary telescopes. Yet its presence is revealed through its gravitational effects. The first hints of this hidden mass appeared nearly a century ago, when astronomers began to measure how galaxies rotate. In the 1930s, Fritz Zwicky studied the Coma cluster of galaxies and found that the galaxies within it were moving too fast to be held together by the gravity of their visible stars. He concluded that some unseen material must provide additional mass, dunkle materie, or dark matter. Decades later, astronomer Vera Rubin and her collaborator Kent Ford extended this discovery to individual galaxies. By measuring how quickly stars and gas clouds orbited in the outer regions of spiral galaxies, Rubin found something astonishing. Instead of slowing down with distance from the center, as expected if most of the mass were concentrated in the visible stars, the rotation speeds remained nearly constant. The outer regions were moving far too fast to be explained by visible matter alone. The logical conclusion was that each galaxy was embedded in a massive halo of invisible material, extending far beyond its luminous disk. The Milky Way follows this same pattern. Observations of stellar motions, globular clusters, and satellite galaxies all indicate that the visible mass, the stars, planets, gas, and dust, accounts for only a small portion of the galaxy's total weight. The rest, perhaps more than 80%, is dark matter. This invisible halo stretches out to at least several 100,000 light-years, enveloping not only the disk, but also the Milky Way satellite galaxies, such as the Magellanic Clouds. Though unseen, it defines the very shape and stability of our galaxy. The evidence for dark matter comes from several independent sources. The motions of stars in the Milky Way's halo and of satellite galaxies orbiting the Milky Way can be measured with precision using instruments like the Gaia spacecraft. These measurements show that the outermost stars move at speeds that cannot be sustained unless a vast amount of mass lies beyond what we can see. Gravitational lensing, the bending of light from distant objects by the gravity of intervening matter, provides further confirmation. When astronomers measure the distortion of light from background galaxies, they can map the distribution of mass along the line of sight. These maps consistently reveal far more mass than is visible, both in our own galaxy and throughout the universe. Despite the strength of this evidence, the nature of dark matter remains unknown. It is not made of ordinary atoms, which interact with light and other forms of electromagnetic radiation. Instead, dark matter interacts primarily through gravity and possibly through the weak nuclear force. The leading candidates are hypothetical particles such as WIMPs, weakly interacting massive particles, or axions, ultralight particles predicted by some extensions of quantum field theory. Other possibilities include sterile neutrinos or even more exotic constructs like primordial black holes formed in the early universe. Yet, despite decades of experiments, no direct detection of dark matter has been confirmed. Physicists have built sensitive detectors buried deep underground, shielded from cosmic rays, in hopes of capturing the faintest interactions between dark matter particles and ordinary matter. They have searched for telltale signals in space, such as gamma rays produced by dark matter annihilations. So far, the results remain tantalizing but inconclusive. Dark matter continues to elude direct observation, hiding in the vast spaces between stars, shaping the cosmos from the shadows. In the Milky Way, the dark matter halo determines much of the galaxy's large-scale structure and evolution. It provides the gravitational framework in which the visible components, stars, gas, and dust, reside. The spiral disk, the bulge, the satellite galaxies, even the paths of intergalactic streams of gas, all move within the deeper gravitational field of the halo. Computer simulations of galaxy formation show that dark matter was the first ingredient to collapse after the Big Bang. As the universe cooled, tiny fluctuations in density grew under gravity, forming halos of dark matter that acted as gravitational wells. Into these wells, ordinary matter fell, forming the first stars and galaxies. In this way, dark matter shaped the cosmic architecture itself. Without it, the universe would look very different, diffuse, structureless, unable to form the rich web of galaxies we see today. In the case of the Milky Way, its halo likely began forming more than 13 billion years ago, gathering gas and smaller halos through mergers and accretion. The visible galaxy we now inhabit, the disk with its spiral arms, the central bulge, and the bright clusters, condensed later within that pre-existing halo of invisible matter. Even today, The Milky Way continues to grow by consuming smaller galaxies, their stars and dark matter streams merging seamlessly into the greater whole. One of the most fascinating aspects of the halo is its possible substructure. Simulations predict that it should contain thousands of smaller clumps, or subhalos, relics of the galaxy's assembly history. Some of these subhalos may host the Milky Way's dwarf satellite galaxies, while others remain completely dark, containing no stars at all. Astronomers search for their gravitational fingerprints by looking for tiny distortions in stellar streams, trails of stars left behind by disrupted clusters or galaxies. These subtle patterns provide clues to the otherwise invisible scaffolding of dark matter that surrounds us. The shape of the Milky Way's dark matter halo is another subject of ongoing research. While early models assumed it to be spherical, more recent studies suggest it may be elongated or slightly flattened, reflecting the complex interactions between the halo and the rotating disk of the galaxy. Understanding its exact shape and density profile is crucial, not only for mapping the Milky Way's mass, but also for refining models of dark matter behavior and the nature of gravity itself. Although dark matter does not emit light, it indirectly influences the luminous parts of the galaxy. Its gravity governs the rotation speed of stars, stabilizes the disk against disruption, and shapes the orbits of satellite galaxies. It even affects the distribution of interstellar gas, helping to maintain the spiral structure by providing an underlying gravitational anchor. In this sense, dark matter is not just a background component. It is the silent framework that makes the Milky Way possible. And yet, despite its dominance, we are effectively blind to it. We live inside the halo, but cannot perceive it. It surrounds us like an invisible ocean, extending hundreds of thousands of light years in every direction. Every atom on Earth, every photon of sunlight, every visible star, all exist within this unseen realm. It is a humbling reminder that what we can observe directly represents only a small fraction of reality. For cosmologists, the dark matter problem is both scientific and philosophical. It challenges our understanding of what the universe is made of. We can describe its gravitational influence with precision, but we do not yet know what it is. It could consist of particles beyond the standard model of physics, or it could hint at a deeper modification to the laws of gravity themselves. Whatever the answer, solving the mystery of dark matter will reshape our understanding of both the universe and our place within it. From an existential perspective, the dark matter halo invites reflection on the limits of perception. Most of the matter that shapes our galaxy is invisible and perhaps forever beyond direct detection. Yet, without it, we would not exist. The sun's orbit, Earth's stability, even the structure of the night sky depend on this unseen mass. The fact that so much of reality is hidden from our senses is not a flaw in our understanding, but an inherent feature of existence. The universe has depth far beyond what light alone can reveal. Perhaps there is something poetic in that. We live inside a galaxy illuminated by billions of stars, yet most of its substance is dark. We are creatures of light, built from the luminous matter of stars, but we are sustained within a framework of shadow. The visible and the invisible coexist, each giving the other meaning. The Milky Way's shining disk floats within an unseen halo, just as consciousness itself floats within the vast unknown of the universe. When you look up at the night sky, every glimmer you see is surrounded by a darkness that is not emptiness but structure. an invisible architecture holding everything together. The stars, like thoughts, are only the visible expression of something deeper and unseen. To understand the Milky Way's halo is to realize that the cosmos is built as much from mystery as from matter. And in that mystery, there is a quiet reassurance. We are part of a universe that is far larger, richer, and more intricate than our senses can grasp. The same unseen gravity that binds the stars also holds us, keeping our fragile world in orbit within an invisible sea. The dark matter halo reminds us that even when we cannot see the forces shaping our path, they are there, silent, enduring, and vast. Chapter 8. Companions and Neighbors, the Local Group and Satellite Galaxies. The Milky Way, magnificent as it appears in isolation, does not exist alone in the universe. Like every great structure in the cosmos, it is part of a community, a small cluster of galaxies bound together by gravity, known as the local group. This family of galaxies, though modest compared to the immense clusters scattered across the universe, defines our cosmic neighborhood. It shapes the Milky Way's motion, its evolution, and its future. To understand our galaxy fully, one must see it as part of this wider network, where interactions between galaxies are as vital to their growth as the stars within them. The local group contains more than 50 galaxies, though only a handful are large enough to be easily visible through telescopes. At its core are three dominant members: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. These three spiral systems hold most of the group's mass, while the rest are smaller dwarf galaxies, faint, irregular, or spheroidal systems that orbit the larger ones like moons around planets. The entire local group spans roughly 10 million light-years across and is held together by mutual gravitational attraction, drifting as a unit through the larger cosmic web. The most significant of our galactic companions is the Andromeda Galaxy, also known as Messier 31. It lies about 2.5 million light-years from us and is the closest spiral galaxy comparable in size to the Milky Way. Andromeda is slightly more massive, containing hundreds of billions of stars, a similar spiral structure, and its own family of satellites. Observations show that it is moving toward us at a speed of several hundred kilometers per second. Far from being a static neighbor, Andromeda and the Milky Way are on a collision course, a slow cosmic dance that will culminate in their merger several billion years from now. When these two galaxies finally meet, their stars will not collide directly, as the spaces between them are vast. Instead, their mutual gravity will warp and stretch their disks, flinging long tidal streams of stars into space. Over time, they will merge into a single, larger elliptical galaxy, sometimes referred to as Milkomata by astronomers. The central black holes of both galaxies will spiral toward one another and eventually coalesce, releasing enormous amounts of energy in gravitational waves. This future merger, though far beyond human timescales, is a natural part of galactic evolution and a reminder that even on cosmic scales, nothing remains unchanged forever. The third major member of the local group, the Triangulum Galaxy, is smaller and less massive than the Milky Way and Andromeda, but still an impressive system of its own. It appears to be gravitationally linked to Andromeda and may be orbiting it in a loose association. The interactions between these three galaxies, Milky Way, Andromeda, and Triangulum, define the local group's central gravitational structure, influencing the motions of the many smaller galaxies that surround them. Orbiting the Milky Way itself is a retinue of dwarf galaxies, our immediate companions. The most prominent of these are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere. These irregular dwarf galaxies are located about 160,000 and 200,000 light-years away, respectively, and are bound to the Milky Way by gravity. They are not static satellites, but are actively interacting with our galaxy, leaving behind a long stream of gas known as the Magellanic Stream, which stretches across much of the southern sky. This stream, composed of hydrogen gas, stripped from the dwarfs by gravitational forces, and the Milky Way's halo, may one day provide raw material for new star formation in our galaxy. The Magellanic Clouds are also notable for their internal activity. They contain vigorous regions of star formation, particularly the Tarantula Nebula in the Large Magellanic Cloud, one of the most active stellar nurseries in the local group. These galaxies are reminders that smaller systems can be dynamic and creative, not mere appendages to larger ones. Their ongoing interaction with the Milky Way provides astronomers with a real-time laboratory for studying how galaxies exchange gas and stars, and how larger galaxies grow by consuming smaller ones. Beyond the Magellanic Clouds lie other, fainter satellites, such as the Sagittarius dwarf spheroidal galaxy, currently being torn apart by the Milky Way's gravity. Its stars form a long, looping stream encircling our galaxy, evidence of a merger already in progress. Several other small dwarf spheroidals, including the Sculptor, Draco, and Fornax galaxies, follow similar fates. They orbit our galaxy at varying distances, gradually losing stars and gas as they spiral inward. These interactions are a normal part of galactic evolution. The Milky Way's halo, the vast, faint sphere surrounding the visible disk, is partly built from the remains of such ancient mergers. Every large galaxy bears these scars, remnants of smaller systems that were absorbed over billions of years. The local group itself is part of a larger structure known as the local sheet, which in turn belongs to the Virgo supercluster, a vast assembly of galaxy groups and clusters bound by gravity on an even greater scale. Yet, despite these immense surroundings, the local group maintains its distinct identity. Within its boundaries, the gravitational pull of its major galaxies dominates, shaping the motions of all its members. The Milky Way and Andromeda sit at the group's center of mass, pulling their smaller companions into orbits that trace the slow, intricate choreography of the group's collective motion. Astronomers have learned much about the local group through careful observation and measurement. Using the Hubble Space Telescope and more recently the Gaia mission, they have tracked the motions of individual stars and galaxies with unprecedented precision. These measurements reveal that the local group is not static, but gradually collapsing under its own gravity. Eventually, the Milky Way and Andromeda will merge to form the core of a new, larger galaxy, while many of the smaller dwarfs will either be absorbed or flung outward into intergalactic space. The local group, like everything else in the universe, is a dynamic system evolving over cosmic time. The study of dwarf galaxies within the local group has also shed light on one of the great mysteries of modern cosmology, the nature of dark matter. Dwarf spheroidal galaxies, though faint and small, appear to contain enormous amounts of dark matter relative to their visible stars. Their slow rotation speeds and gravitational binding require far more mass than what can be accounted for by luminous matter alone. These small galaxies thus serve as natural laboratories for understanding how dark matter behaves on small scales and how it influences the formation of galaxies. Interactions between galaxies also play a crucial role in the exchange of gas and the creation of new stars. Tidal forces can strip gas from dwarf galaxies, feeding the halos and disks of larger galaxies like the Milky Way. In turn, gravitational encounters can trigger bursts of star formation as gas clouds are compressed. Such processes are not rare or violent exceptions, but continuous acts of galactic recycling. Through these interactions, the local group remains alive and evolving, each galaxy influencing the others in subtle ways. Seen as a whole, the local group represents a microcosm of the universe's larger structure. Galaxies forming, merging, and reshaping each other under gravity's guidance. It is a reminder that galaxies are not isolated islands, but participants in a vast cosmic web, connected across space by invisible filaments of matter. The motions of the Milky Way, Andromeda, and their satellites reflect the same fundamental forces that sculpt clusters and superclusters across the cosmos. From a human perspective, this interconnectedness is both humbling and profound. The light that reaches our telescopes from Andromeda began its journey over 2 million years ago when early humans were first walking the Earth. The interactions that will one day unite our two galaxies are already written in their motions. We are witnessing the universe not as something frozen in time, but as an unfolding story. One chapter in an infinite sequence of creation and transformation. When you look at the night sky, some of the faintest smudges of light, the Magellanic Clouds from the southern hemisphere, or the distant blur of Andromeda, are more than celestial ornaments. They are our neighbors, part of the same gravitational family that carries us through space. The distances between galaxies are enormous, but gravity binds them as firmly as the atoms within our bodies are bound by electromagnetic forces. Everything that exists is connected, from the stars in your sky to the galaxies beyond them. And in that realization lies something timeless. The Milky Way, the Andromeda Galaxy, and all their companions are engaged in an endless dance, moving, merging, and reshaping each other in slow cosmic rhythm. We are part of that dance, bound within the same web of gravity that holds the galaxies together. Though our lives occupy only a brief moment of this grand choreography, the motion continues, quiet and certain, carrying us forward through the universe. To understand our galactic neighbors is to glimpse our own future, and to see, perhaps, that even in the boundless dark, we are never truly alone. Chapter 9. The History and Evolution of the Milky Way. The Milky Way, like every galaxy in the universe, has not always existed in the form we see today. It is the result of more than 13 billion years of cosmic evolution, an immense story of gravity shaping matter, of stars forming and dying, and of countless collisions and mergers that gradually built the vast spiral we now call home. To understand the Milky Way's history is to trace the slow unfolding of cosmic structure from the aftermath of the Big Bang to the present moment, and to glimpse the processes that will continue shaping it long after we are gone. In the beginning, the universe was almost perfectly uniform. About 380,000 years after the Big Bang, matter and radiation decoupled, allowing light to travel freely through space. Tiny fluctuations in the density of matter, imprinted in that early radiation, served as the seeds of all future structure. Over time, under the influence of gravity, these slight irregularities grew, attracting more matter and forming the first dark matter halos. These invisible gravitational wells became the scaffolding for the first galaxies. The earliest stages of the Milky Way's formation began within one of these primordial halos. Cosmological simulations and observations suggest that small proto-galaxies, clumps of gas and dark matter, began to merge together around 13 billion years ago, just a few 100 million years after the first stars ignited. These small systems formed the first generation of stars, known as population 3 stars, made almost entirely of hydrogen and helium. They burned hot and lived briefly, exploding as supernovae that enriched their surroundings with heavier elements. Out of these enriched remnants, new generations of stars formed, creating the first building blocks of what would become the Milky Way. As these protogalaxies merged, they built a larger and more massive structure. The earliest core of the Milky Way likely resembled an irregular blob of gas and stars rather than a disk. Collisions between smaller systems were frequent and chaotic. Over time, as angular momentum accumulated from these interactions, the gas began to settle into a rotating disk, forming the foundation of the galaxy's current shape. The oldest stars we observe today in the halo and in globular clusters are relics from this early epoch. Their chemical compositions, poor in heavy elements, preserve the record of the galaxy's infancy. The Milky Way's growth did not stop once it acquired its basic form. Throughout its history, it has continued to merge with and absorb smaller galaxies. Astronomers can still see the remnants of these mergers today, long streams of stars stretched across the sky, the fossilized trails of ancient collisions. One of the most prominent of these is the Sagittarius stream, the remains of a dwarf galaxy currently being torn apart and assimilated by the Milky Way's gravity. Other faint stellar streams trace similar histories, each one a chapter in the ongoing story of galactic accretion. From about 10 billion years ago onward, the Milky Way entered a relatively stable phase. Its disk thickened as new stars formed, and its spiral structure began to emerge. This period saw intense star formation, fueled by abundant gas drawn in from the surrounding intergalactic medium. The galaxy's chemical composition grew richer with each generation of stars, as supernovae seeded the interstellar medium with carbon, oxygen, and iron. These elements would later become the building blocks for planets and eventually for life itself. The central bulge of the Milky Way, a dense concentration of older stars near the galactic core, also formed during this time. It likely arose through a combination of early mergers and internal evolution, as gas and stars were funneled inward by gravitational instabilities in the young disk. At its center, the supermassive black hole Sagittarius A star grew alongside the bulge, feeding intermittently on gas and smaller objects. The connection between black holes and galactic bulges is a pattern observed across the universe, an indication that the growth of galaxies and their central black holes are intimately linked. Over the next several billion years, the Milky Way's spiral arms became more pronounced. These arms are not fixed structures but density waves, regions where stars and gas bunch together as they orbit the galactic center. They act as engines of renewal, compressing interstellar clouds and triggering new bursts of star formation. The Orion Spur, where the Sun resides, is one such feature. The Sun itself formed about 4.5 billion years ago from a molecular cloud enriched by generations of previous stars. It was born in the midlife of the galaxy, inheriting a stable orbit in the disk and a chemical composition that reflects the Milky Way's long history of cosmic recycling. The present-day Milky Way is still evolving. Observations from the Gaia spacecraft reveal ripples and waves in the stellar disk, evidence of past interactions with satellite galaxies. These perturbations show that even now, the galaxy is not in perfect equilibrium. Streams of stars continue to flow into the halo, and the gravitational tug of the large and small Magellanic Clouds subtly distorts the Milky Way's outer regions. The galaxy remains an active participant in its cosmic environment, not a finished structure, but a living, changing system. Looking into the future, astronomers predict that the Milky Way's most dramatic transformation lies ahead. The Andromeda Galaxy, currently about 2.5 million light-years away, is moving toward us. In roughly 4 billion years, the two galaxies will collide. Their mutual gravity will tear apart their spiral arms, scattering stars and gas into vast tidal tails. Over the next several billion years, they will merge into a single, larger elliptical galaxy. The Sun, by then nearing the end of its life, will drift into a new orbit within that combined system. This merger will mark the next great chapter in the Milky Way's story, one written on timescales that dwarf the entire history of life on Earth. The Milky Way's evolution is not unique. It follows the same cosmic principles that govern all galaxies: formation through collapse and accretion, enrichment through stellar evolution, and transformation through interaction. Yet, because we live within it, we can study its structure and history in far greater detail than any other. Through observations of ancient stars, stellar streams, and the motions of gas, we can reconstruct the invisible steps of its growth. The Gaia mission, for instance, has allowed astronomers to map the precise orbits of more than 1 billion stars, revealing the fossil record of long-vanished galaxies absorbed by our own. Each star's chemistry and motion tell part of the story: where it was born, how it moved, and what it has endured. Some of the oldest known stars in the Milky Way are more than 13 billion years old, nearly as ancient as the universe itself. Their compositions show almost no heavy elements, suggesting they formed from the pristine gas left after the first supernova enriched the cosmos. These stars serve as time capsules from an era when the Milky Way was still assembling its first components. Their continued existence in the halo is a testament to the galaxy's longevity and the stability of its gravitational structure. Even the dark matter halo surrounding the Milky Way tells a story of history and evolution. It was the first part of the galaxy to take shape and remains the framework within which all visible matter resides. The halo's growth through mergers mirrors the assembly of the visible disk and bulge. In many ways, the Milky Way is the luminous face of a much larger invisible system that has evolved in parallel since the dawn of time. From the perspective of cosmic history, the Milky Way is now middle-aged. It has formed most of its stars, and its overall rate of star formation is declining. Over the next tens of billions of years, as gas supplies dwindle and stellar birth slows, the galaxy will gradually fade. Eventually, the remaining stars will age into white dwarfs, neutron stars, and black holes. The Milky Way will become a quiet, dim system, its bright spiral arms long gone. Yet even then, its structure will persist, a fossil of light in a universe growing ever colder and darker. To think of this timeline is to confront both immensity and intimacy. Our planet, our species, and everything we know occupy only a heartbeat of the Milky Way's existence. The atoms that make up your body were forged in stars that lived and died billions of years before the sun was born. You are part of a story that began long before human memory and will continue long after. When you look at the night sky, you are witnessing the latest frame of an ancient film still in motion. The light that reaches you tonight began its journey before our species existed, before civilization, before language. It carries within it the record of the Milky Way's evolution, of countless stars that lived and perished to make your world possible. And in that understanding lies both humility and wonder. The Milky Way's history is not merely the history of a distant structure, but the foundation of everything familiar. Its collisions, its stars, its invisible halo, all of it converged to create the conditions for life and consciousness to emerge. We are, in a sense, the galaxy reflecting on its own past. The same gravity that shaped its spiral arms also holds you here, beneath its starlit disk, thinking about where you came from. The Milky Way story is your story, a reminder that in the grand history of the universe, you have always been home. Chapter 10. The Meaning of Home. The Milky Way as a Mirror of Existence. When we speak of home, we usually mean something close, something familiar, a room, a city, a planet. Yet, on a cosmic scale, our true home extends far beyond the boundaries of Earth. The Milky Way is not just the galaxy that contains us. It is the context that gives our existence shape and meaning. Every atom in our bodies, every element that forms our world, and every beam of light that warms us belongs to this single, vast structure. To understand the Milky Way scientifically is to uncover the deep continuity between ourselves and the universe, to see that we are not merely living in the galaxy, but are of it. From a physical perspective, the Milky Way is a dynamic system, a rotating disk of hundreds of billions of stars, gas, and dust, all embedded within an even larger halo of dark matter. It is one of trillions of galaxies in the observable universe, and yet to us, it is unique, the galaxy through which we view all others. It has existed for more than 13 billion years, growing and changing as it merged with smaller systems and formed new generations of stars. In its present form, it stretches across more than 100,000 light years, a spiral of light and shadow turning endlessly in the dark. This structure is both ancient and alive, shaped by the same fundamental forces that govern the behavior of matter everywhere. The concept of home in this cosmic sense is not sentimental but structural. The Milky Way provides the gravitational environment that sustains our solar system's orbit. Without it, the sun and its planets would not move in a coherent path. Earth would not experience the stable conditions necessary for life. The galaxy's dark matter halo holds the stars together, while its spiral arms continue to recycle gas and dust into new suns and worlds. Our planet is one of countless possible outcomes of this ongoing galactic metabolism. The light from the Milky Way that reaches our eyes on a clear night is a cross-section of this immense structure. It is the collective glow of stars scattered across tens of thousands of light years, their light blending into a silvery band that encircles the sky. What we see as a tranquil ribbon of light is, in fact, a momentary glimpse into a vast rotating system, a panorama of motion, birth, and decay. The serenity we perceive is the illusion of scale, the calm that comes from watching a process so immense that its movement unfolds over eons. Science allows us to see beyond this illusion. The Milky Way is not static, it is constantly changing. Stars form within cold molecular clouds, live their lives for millions or billions of years, and then die, enriching the galaxy with heavy elements. Supernovae blast shockwaves through interstellar space, compressing gas into new star-forming regions. Stellar winds carve bubbles in the surrounding medium, and gravitational tides draw streams of stars from nearby dwarf galaxies. Even the spiral arms are not fixed structures, but patterns of density waves, moving through the disk like ripples across a pond. The Milky Way is not a place but a process, a continuous flow of energy and matter through time. Humanity's understanding of this process has evolved dramatically in just a few centuries. For most of our history, the Milky Way was an enigma. Ancient civilizations saw it as a pathway for spirits or gods, a celestial river, or the spine of the night. Only in the early modern era did telescopes reveal that the faint glow was composed of countless stars. In the 20th century, astronomers discovered that the Milky Way itself was only one of many galaxies, and that all are receding from one another as the universe expands. With the advent of radio and infrared astronomy, we learned to peer through the dust, mapping the galaxy's spiral arms, its central bar, and the dense molecular clouds that give rise to new stars. Missions like Gaia now chart the precise motions of billions of stars, transforming our understanding of the Milky Way from a static picture into a dynamic, living model. From these observations, we know that the Sun and its planets are relatively young participants in the galaxy's long history. Our solar system formed about 4.5 billion years ago from a cloud of gas enriched by earlier generations of stars. The heavy elements that make up Earth's crust, oceans, and living creatures were forged in the hearts of those long-dead stars. Carbon, oxygen, iron, all were created in nuclear reactions that occurred billions of years before the solar system existed. In this sense, the Milky Way is our ancestor. Its cycles of creation and destruction are the direct cause of our existence. The Milky Way is also our frame of reference in space. When astronomers measure the position of any celestial object, they do so relative to the galactic plane. The galaxy provides the coordinates that define our orientation in the universe. Even our perception of the night sky, the constellations we draw, and the myths we create, is shaped by our position within the disk. The stars that seem close together in constellations are, in reality, scattered across thousands of light years, their apparent patterns defined only by our viewpoint within this single galaxy. Yet the Milky Way is not permanent. Astronomical evidence shows that galaxies are transient entities constantly evolving. In a few billion years, the Milky Way will merge with the Andromeda Galaxy, forming a new, larger system. The spiral arms will be torn apart, the central black holes will merge, and the resulting galaxy will shine for trillions of years before its stars grow dim. Long after our sun has faded, the atoms that once formed Earth, and perhaps the remnants of whatever follows humanity, will still orbit within that future system. Even as forms change, the matter remains, part of the unbroken continuum of the galaxy's existence. To call the Milky Way home is therefore not merely a statement of location but of identity. It defines the scale at which we belong to the universe. We are not separate from it, nor passengers within it. We are expressions of its ongoing processes. The iron in our blood was once in a star's core. The calcium in our bones was forged in a supernova. The atoms of our bodies have traveled through time and space, from the birth of the galaxy to the formation of the Earth, and will continue their journey long after we are gone. The Milky Way is both the cradle and the grave of matter, the setting in which consciousness, for a brief moment, became aware of itself. The notion of home also carries emotional weight, even in scientific terms. In astronomy, the Milky Way serves as a baseline for understanding other galaxies. Every observation of distant systems, spiral, elliptical, or irregular, is interpreted through comparison to our own. By studying the Milky Way, we calibrate our understanding of the universe. The patterns we find here, of star formation, chemical evolution, and gravitational interaction, echo throughout the cosmos. Our home galaxy is both unique in its details and universal in its principles. It is a mirror in which the universe reflects its own structure and history. In philosophical terms, the Milky Way embodies the paradox of existence. We are tiny and temporary, yet made of the same materials and governed by the same laws as the stars. The distances that separate us from other systems are immense, but the physics that connects us is universal. The galaxy's light stretching across the sky is a visible symbol of that unity. Countless suns bound together by gravity, moving in harmony through the darkness. There is also an existential humility in recognizing that most of the galaxy is not visible to us. The luminous matter we see represents only a small fraction of its true mass. The rest, the dark matter halo that envelops the Milky Way, remains hidden, shaping its structure from beyond the reach of light. We live surrounded by the unseen, sustained by forces we can measure but not directly perceive. In that sense, the galaxy is a metaphor for knowledge itself. What we understand is illuminated by light, but what truly sustains us lies in the dark. The Milky Way's story, from its chaotic beginnings to its serene spiral form, mirrors the broader arc of the universe. From simplicity to complexity, from energy to structure, from chaos to order. And within that order, life emerged. Fragile, transient, yet capable of reflection. The same physical laws that govern the rotation of galaxies also govern the chemistry of the brain, the motion of thoughts, and the formation of memory. To look at the Milky Way is, in a sense, to look inward, to see the larger pattern of which consciousness is a fleeting but meaningful expression. Perhaps that is the ultimate meaning of home on a galactic scale. It is not merely the place where we live, but the system that made living possible. The Milky Way is not distant or abstract. It is the field in which every atom of our being participates. We are the galaxy, thinking about itself, just as a wave is part of the ocean that creates it. When the night is clear, and the Milky Way stretches across the sky like a bridge of light, you are seeing the collective memory of the cosmos. Light from billions of suns, some alive, some long dead, all still connected through gravity and time. It is a vision of continuity that transcends the fragility of human life. We may be small, but we are not insignificant. Our existence is one thread in the tapestry of the galaxy, woven from the same material that fills the stars. And in that quiet realization, there is a kind of peace. The Milky Way is vast, ancient, and ever-changing, yet it carries us effortlessly through space, just as it has carried generations of stars before us. To call it home is not to claim possession, but to recognize belonging. To know that, in this immense and luminous structure, we are both fleeting and eternal, both the observers and the observed. You've traveled across the galaxy, my friend, through light, dust, and time itself. If you're still awake, there's another journey waiting for you. Just let it play and keep drifting among the stars. And if your eyes are closing now, sleep well, dream deep, and remember, you are made of starlight.